container with most water looks quadratic at first, but one greedy rule gives us a linear solution. Move the shorter wall inward. We need the two lines that maximize width times the shorter of the two heights. You are given an integer array height of length n. There are n vertical lines drawn such that the two endpoints of the ith line are I, 0 and I, height I. Example 1 ends with answer 49. The above vertical lines are represented by array 186254837. In this case, the max area of water blue section the container can contain is 49. Example 2 ends with answer 1. The important sizing limits are n equals height dot length, 2 lesser equal n lesser equal 105, and 0 lesser equal height I lesser equal 104. This is a proof by bottleneck idea. The shorter wall caps the water level, so moving the taller wall cannot help enough to beat what we already know. Area depends on width times min left height, right height, so the shorter wall is the bottleneck. So in practice, if we move the taller wall, width shrinks and the bottleneck does not improve. So the only useful gamble is moving the shorter wall, and that is why two pointers work here. The example is all about trusting the invariant that the shorter wall is the only pointer worth moving. In the classic example, the best container uses indices 1 and 8 for area 49. So the walkthrough goes in order. First start from the full width, then shrink from the shorter side only, and finally keep the best area seen so far. For the deeper version, the important thing is not more code first. It is naming the invariant that makes every local move safe. The long version should pause on the invariant or the local rule that makes the solution reliable, not just on the final code. So in practice, name the rule that stays true while scanning. Connect that rule to the pointer or state movement, and then the implementation feels natural. The code updates the best area, then uses the shorter wall rule to decide which pointer moves. In the code, focus on two checkpoints. Watch where the answer updates inside the loop, then notice which value is returned to finish the reasoning. Here is the full solution. The entire correctness argument lies in the decision to move only the limiting side. In the code, focus on two checkpoints. Watch where the answer updates inside the loop, then notice which value is returned to finish the reasoning. Because each pointer only moves inward, the algorithm is linear time and constant space. Both pointers move inward once. So in practice, time complexity, O(n), extra space, O1, and this is a classic greedy two-pointer contraction pattern. For more LeetCode practice, follow and subscribe to the channel. This is AI and human collaboration.